Hello everyone, let's discuss the acquisition and understanding of some formulas of relativity. Let's draw a celestial body. This is a celestial body with mass m. We use capital M to represent. Its mass is m. Then let's imagine an object again, an object from infinity, approaching the celestial body, which is under the gravitational pull of this celestial body, towards this celestial body. The object we are virtualizing is represented by a lowercase m, is an object with mass mo, approaching it under its gravitational pull. It starts to approach it from a speed of 0. We assume that it has reached this position. After a long time, the celestial body has come to this position, which is at a distance of r. It acquires a speed v under the influence of its gravity. It has a speed v in this direction. Under the influence of its gravity, the speed of the object increases from 0 to v. Then the object is no longer in a static state. It has a certain kinetic energy. According to special relativity, we can know that it has a mass of motion. Its moving mass. Let's assume it is m. From this celestial body, the mass at infinity is m0. At an infinite distance from celestial body m, the rest mass of this object is mo. Now it is r away from the celestial body, and its velocity is v. It has a certain kinetic energy. That is, it has a certain amount of moving mass. Its mass in a moving state is denoted by m. M is his mass in a state of motion. The velocity and the rest mass. The relationship between the three is m equals. This is the mass formula in special relativity. This is the relationship between the three. M is the moving mass, and mo is the rest mass. That is, the rest mass at infinite distance from the celestial body. This v is the moving speed of the celestial body, and c is the speed of light. Then we know that not only its mass is changing, but also the time running speed of the object itself is also changing. Suppose is at an infinite distance from the celestial body. Its time flow rate is t0. Let's use t0 to represent it. And now it has a velocity of v, and it is r away from the celestial body. Its time passes at t. The relationship between them is, this is the time in the moving state. This is the time in the static state. This is the motion speed. The relationship between them is like this. This is the time formula of special relativity. We also know that its length will also change in the direction of motion. Its length will change. Its length in the static state is assumed to be L0, and the length in the moving state is represented by L. We can form another relationship. Its relationship is like this. L equals L0 times root of 1 minus v squared over c squared. This is their relationship. These three formulas are the three basic formulas derived from special relativity. This is the mass formula in special relativity. This is the time formula. This is the length formula. An object with a velocity of v, its kinetic energy is. We know the kinetic energy formula is 1/2 mv squared. This is the kinetic energy formula. This m can be either this m or this m0. When the speed is relatively small, we can equate these to masses. This is the kinetic energy formula. This is the kinetic energy it has at this time. So what about its gravitational potential energy? It came here from an infinitely far place. What is the change in its potential energy? Or what is the amount of its gravitational potential energy? Its gravitational potential energy formula. We know that. This is the formula for gravitational potential energy. There is a negative sign in front. This negative sign represents that, which means the gravitational potential energy is decreasing. In fact, it is. To this position, this r is this r. This mass m is this mass m. This m is the m and mo here, under the action of gravity. The change in its energy. This is the change in its energy. This is the total change in its gravitational potential energy. The change in gravitational potential energy. That's how much its gravitational potential energy has changed. At infinity, this r will be infinitely large. and the gravitational potential energy is 0. So, this position represents its gravitational potential energy. From 0 to a certain value is the change in gravitational potential energy. The closer to the celestial body, the smaller its gravitational potential energy is. In fact, they are equal. They are equal. Its kinetic energy is transformed from its gravitational potential energy. The two values are equal. Is the decrease in its gravitational potential energy is converted into its kinetic energy. We combine these two formulas. 0.5 times the square of mv equals gm divided by r. Okay, we can set them equal because they are actually equal. Then we can eliminate these to lowercase m's. Then only the square of v remains here, equal to 2 times gm divided by r. This is the escape velocity. The square of the escape velocity is equal to it. Escape velocity is actually from an infinite distance. By this point, the speed obtained, the reverse process, is actually the escape velocity. So this v and this v are equal. They are equal. They are the same v. We know that. The v in this formula is the same as this v. This v is still this v, and this v is also this v. So we can substitute the square of v into this formula. Can be completely substituted because they are the same thing. Let's look at the common substitution formula results. For example, these two here are. This is the formula of time dilation in special relativity. This is the formula we get after substitution. This mass is its mass, the mass of large celestial bodies. This r is this r, the gravitational constant g, the time during which an object is in a state of motion. Actually, it can be transformed into time in the gravitational field, because it is indeed here. Its time is indeed like this. So, the time here, we can consider it as the time in the gravitational field. That is to say, we no longer consider its speed. We consider its position in the gravitational field. It is affected by this celestial body. When it is at this position, its time in the gravitational field is like this. The time effect of an object's motion speed can be transformed into time in a gravitational field. This time can also be changed to the time in the gravitational field. At this point, this time is time at an infinite distance from the celestial body. The time here is the time at a location that is at a distance r from this celestial body. Then this length becomes the length in the gravitational field. This length is the length from the infinite distance from the celestial body. So this time, this formula actually becomes the length in the gravitational field. So this length becomes the length in the gravitational field. This length is the length at a place where the distance from this celestial body is r. Of course, we are very familiar with these two formulas. This is the time formula given by general relativity. This is the length formula given by general relativity. They can all pass through the gravitational field equations of general relativity by a series of simplifications. These formulas are not approximate formulas, but simplified formulas. It means simplifying or specializing the conditions to obtain these formulas. This is the more common one, which is t equals t0. This is the time formula in a gravitational field. This is the length formula in the gravitational field. These are two common formulas. Okay, this process. This is derived by another method. Time and length formulas in the gravitational field. Actually, that was just our thought process. It is derived in this way, or it can be derived in this way, without deriving from the equation of the gravitational field. It can be derived like this. This is the formula derived following this line of thinking. Of course, we have not seen another formula. We also put this thing, the square of v, we substitute it into the mass formula, and see what happens. Okay, this formula seems not to have been seen before. M is the mass in the gravitational field. This is the mass in the gravitational field. The mass in the case of zero intensity. This is the mass of celestial bodies. This is the mass. This r is this r. So, we have obtained the mass formula in the gravitational field. Let's write it down here. Its mass formula is m equals. Okay, this is the mass formula in the gravitational field. You have almost never seen such a formula. Does this formula have any meaning? In fact, it is the same as these two formulas. If these two formulas are meaningful, then this formula is also meaningful. Let's take a look. From an infinitely far place, its mass is mo, and it moves here. It has a certain kinetic energy. In fact, we know that. Kinetic energy can be expressed by mass, which is kinetic energy divided by the square of the speed of light. Kinetic energy divided by the square of the speed of light is mass, so it represents its moving mass. That is to say, if it starts from 0 speed and moves from infinity to here, its moving mass is m, or its mass in the gravitational field is m. Then if it is closer, its mass will continue to increase. This is very natural. Some say if it doesn't start from 0 speed, such as if it has an initial velocity. How to calculate? In fact, it has an initial velocity. It has kinetic energy. The kinetic energy can still be converted into mass, which is the mass of m0. It can still be done. Convert the kinetic energy into mass of m0. It can still be calculated like this. If it is approaching this celestial body, it collides with other objects or experiences forces. Its energy is lost. Can we use this formula? In fact, it can still be. Because its mass has been lost, it will be converted into mass in other places. Yes. In fact, we can all virtualize its mass. In fact, its mass has not changed. Because it's just that its mass is dispersed. So this formula is still correct. It's this formula. Its correctness is equivalent to these two formulas, or have the same degree of correctness. The degree of correctness of these two formulas. It has the same degree of correctness. Let's approximate this formula. Let's see how. We know that, when the value of this area is far less than 1, we can remove the square root from the formula. Let's see, m equals 1 minus. Okay, this is what the formula after removing the square root. When this part is far less than 1, we can use this approximate formula. This is an approximate formula. We transform this approximate formula. After transformation, we get this formula. This is the mass in the gravitational field. This is the mass at the place where the gravitational field is 0. The mass in the gravitational field minus this mass equals it. What is this thing actually? Look, we can find that it is very similar to it. It's this. They are very similar. This is actually the gravitational potential energy. This part is actually the gravitational potential energy. Its energy. Energy divided by the square of the speed of light is mass. Mass minus mass equals mass. This formula is very consistent with our common sense. So it is likely that this formula is correct. If these two formulas are correct, the formula we get is also correct. This is its approximate formula. The connotation of this approximate formula. It is the change in its energy in a gravitational field. The change in energy is proportional to the mass. Is that the change in energy is proportional to the mass? And this, inversely proportional to this r. The closer it is to the gravitational source, the greater its energy is. The closer it is to the gravitational source, the greater the change in its mass. The greater the change in mass in the gravitational field. We can see from here that is the change in its mass, and their relationship is proportional to the mass change, is proportional to the mass of the celestial body, inversely proportional to the radius r. This is a simple and approximate formula. It is an approximate formula under the condition that the gravitational field strength is not large. If the gravitational field intensity is high, or the celestial body is massive, then this approximation cannot be used. Then we still use this formula. Facing this formula, we will all feel. We will feel extremely confused. We know that this is the Schwarzschild radius. This part is the Schwarzschild radius. When the value of this area is equal to this radius, it will be infinite. Its mass will be infinite. Any celestial body, any object approaching this celestial body. Once it reaches the Schwarzschild radius, the change in its mass will reach infinity. This is beyond our imagination. We know that these masses cannot be infinite. Although it leads to the same conclusion as such a formula, its time will be infinitely slow, and its length will shrink infinitely. But it doesn't shock us much, because time seems to be infinitely slow. We can seem to accept this reality. But if its mass is infinite, we cannot accept it. For example, a pen approaching a black hole to the Schwarzschild radius. When it reaches the surface of the black hole, its mass will become infinite, which is really beyond our imagination. If we take any object close to the black hole, its mass will reach infinity. We really cannot accept this conclusion. But according to this formula, it is like this. It shows that this formula and this formula, they are formulas of the same level. This formula is likely to be wrong. It's just under the condition where the gravitational field strength is relatively small, is correct, or close to correct. This is the same. That is to say, in the case of a weak gravitational field, we can use such formulas to calculate. From here, we can deduce that. That is to say, we can imagine that this formula is wrong. Similarly, this formula is also wrong. This formula is also wrong. That is to say, through general relativity, these formulas derived from general relativity are wrong. They only apply to weak gravitational fields and moderate gravitational fields. In weak or moderate gravitational fields, these formulas can be used. It means that in the process of deriving these formulas, there are flaws. We know that their flaws are very obvious, because the formula for gravitational potential energy is obtained under the assumption that its mass remains constant, but in fact, its mass is changing. The mass remains constant, but the mass is changing. So, this gravitational potential energy formula should be modified. This is a changing mass. The formula for gravitational potential energy must be modified. But this mass is actually also changing. But if they are modified proportionally, they can be cancelled out, which seems to be okay. But in fact, they are not quite the same. The mass of this mass, it seems that the range of change in quality is different from this. In fact, this kinetic energy formula under high-speed conditions, and close to the speed of light, this kinetic energy formula is inaccurate. It is incorrect. This kinetic energy formula itself is an approximation. It itself is an approximation formula for low-speed motion. In the case of low-speed motion, using this formula is correct. In the case of high-speed motion, using this kinetic energy formula is wrong. The real kinetic energy formula is mc squared. This is the real kinetic energy formula. So this kinetic energy formula is actually approximate. Okay, that's all for today.